Okay, let's unpack this. You know how sometimes adding just one more rule, or maybe one more condition, doesn't just make something a little bit harder.
Ah,
It can suddenly make it fundamentally different, or maybe even impossible. Like there's this specific moment, a tipping point, where everything just changes.
yeah. Think about building a house of cards. Adding one more card carefully is fine, usually.
Right.
But adding just enough cards, maybe in just the wrong places, the whole structure doesn't just get more wobbly, it collapses completely. It's a totally different state.
That's exactly the kind of surprising shift we're diving into today.
Okay.
We're exploring a study that looks at this precise phenomenon, this dramatic tipping point, but in the world of computer science,
Right.
specifically the satisfiability problem, or SAT.
Aha, SAT. Okay.
Our source material is a research paper. It's titled Exploring the Emergence Threshold in SAT Problems, Investigating Solution Generation from Constraint Accumulation and, the experimental data that goes with it.
Got it. So our mission for this deep dive is to really understand this idea, this critical threshold in SAT problems.
hmm
We'll walk through the findings from this specific experiment, and I think this is the really interesting part. Dig into the connections the study makes.
Connections.
Yeah, between these like abstract computational problems and the kind of sudden emergent changes we see in complex systems all over the place.
Oh, interesting. Like physics or even social structures.
Exactly.
All right, so before we get to tipping points, let's ground ourselves a bit. What exactly is the satisfiability problem?
Okay. So at its heart, SAT is a really fundamental decision problem.
The decision problem.
Yeah, you're given a logical formula. It's made up of variables that can only be true or false, what we call Boolean variables.
True or false, that's it.
Right. And the question is simple. Can you find any combination of true-false assignments for those variables that makes the entire formula evaluate to true?
Okay, so you're just looking for one way to satisfy the whole thing. Not always, just a way.
Precisely, yes. Does a solution exist? And these formulas, they're usually written in a standard format. It's called conjunctive normal form, or CNF.
CNF, right.
This just means the whole formula is a series of AND statements linked together.
Mm.
And each of those AND parts, we call them clauses, is itself a series of OR statements.
So inside the clauses, it's ORs. Connecting the clauses, it's A and Ds.
You got it. And the things being ORed together are the variables, or maybe they're negations, not X, for instance. We call those literals.
So something like by 1 or not by 3 or by 5, ND, not by 2 or by 4, that would be a formula in CNF.
Perfect example. Yes.
And SAT is asking, is there some true-false setting for by 1, by 2, by 3, by 4, by 5 that makes both of those bracketed parts true?
That's exactly the question. Now, why is this seemingly simple thing such a big deal?
Yeah, why focus on this?
Because SAT is what's called NP complete. This is huge in computer science.
NP complete. I've heard that term. It means it's hard, right?
It means it's among the hardest problems in a very important class called NP. Back in 1971, Stephen Cook proved SAT was the first problem shown to be in this special category.
The first one. Wow.
Yeah. And the key thing about NP-complete problems is that many, many other hard problems can be sort of translated or reduced into SAT.
So cracking SAT is like having a master key.
Kind of, yeah.
Yeah.
If you could find a genuinely fast way to solve any SAT instance, you could theoretically solve a huge number of other really difficult problems efficiently, too.
Problems in like logistics or design or...
All sorts of things.
Yeah.
Circuit verification, software testing, planning, scheduling. The list goes on. Understanding SAT is absolute fundamental. It even touches on that huge, famous P versus NP question.
The million-dollar question.
That's the one. And yeah, it's not just theoretical. SAT solvers are practical tools used every day.
Okay, so SAT is important. We have variables and we have clauses that act like rules or constraints.
Right.
And this study, it zeroes in on something called constraint density.
Yes, this is the key parameter they play with. Constraint density, usually written as R,
Right.
it's just a simple ratio. The number of clauses, let's call it M, divided by the number of variables, N. So R expand N.
Okay, simple enough. So a higher R just means you have more clauses, more constraints for the number of variables you're working with.
Exactly. More rules relative to the things you're trying to assign values to.
Right.
And think about the total number of possible true-false assignments. For N variables, it's 2 to the power of N.
Which gets enormous really fast.
Incredibly fast. That's your entire universe of potential solutions. Now, each clause you add, each constraint,
It cuts down the possibilities.
this acts like a filter. It says, okay, these specific combinations of true-false values aren't allowed if you want to satisfy me.
So adding more clauses, increasing R, means you're ruling out more and more assignments from that big two-head universe.
Exactly. The space of potential solutions shrinks. It gets narrower.
And you might think, okay, it just gets harder and harder to find a solution as you add rules. Maybe the number of solutions just smoothly drops off until it hits 0.
That seems intuitive, right? Just a gradual decline. But that's not what tends to happen with random SAT instances.
Ah, okay, and that's where this whole idea of a critical threshold comes in.
Precisely. People noticed through experiments and theory that the likelihood of a random SAT instance having any solution at satisfiability doesn't just decrease gently as you increase R.
It does something else.
It seems to stay pretty high for a while, and then suddenly it plummets very, very sharply around a specific value of R.
A sudden drop, not gradual.
Right. And that sudden change is what made people think of things like phase transitions in physics.
Like water suddenly freezing into ice at 0 degrees Celsius, not gradually getting slushier and slushier over a wide range.
Exactly that kind of sharpness. Or how complex systems can suddenly flip into a new mode of behavior.
So the parallel is, it's not just getting harder, the nature of the problem seems to change abruptly.
That's the idea this study explores, it asks. As these constraints pile up, do you hit a specific emergence point, a critical constraint density, beyond which solutions basically just vanish? And can we measure this point accurately?
Okay, and the study focused specifically on 3SAT you mentioned.
Yes. 3SAT is where every single clause has exactly 3 literals.
Why 3SAT?
Well, it's kind of a standard. It's still NP complete, so it represents the difficulty of the whole class, but it's structured enough to be studied experimentally. And previous work had already estimated this sharp transition for random 3SAT happens somewhere around order 4.26.
4.26, okay, a specific number.
Yeah, an empirical estimate. So this paper wanted to really probe that specific region experimentally and see how it behaved for different problem sizes, different numbers of variables.
Okay, so how did they actually set up the experiment to look for this threshold? What did they do?
Their approach was pretty straightforward conceptually. Generate lots and lots of random 3SAT problems. And then systematically vary that constraint density R and see how 2 things change. First, whether the problems have solutions, and second, how long it takes a standard solver to figure that out.
What sort of scale are we talking? How many variables? What range of densities?
They varied the number of variables in it. They used sizes like 20, 40, 60, 80, and 100, so increasing sizes.
Okay.
And for the constraint density R, they swept it across the interesting region, going from RO goals 2.0 all the way up to 6.0.
And covering that predicted 4.26 value.
Exactly. They took measurements in steps of often 1 for R, so 2.0, 2.1, 2.2, and so on, up to 6.0.
And for each specific combination, like N60 and RWOL's 4.2, what did they do?
For every single one of those under pairs, they generated 100 unique random 3SAT instances.
100 samples for each point.
Right, using a standard random generation method.
Yeah.
For each clause, pick 3 distinct variables at random from the n available. Then, for each of those 3 variables in the clause, flip a coin, 50% chance it's included normally, like by 1, 50% chance it's negated, like not by 1.
Okay, so a well-defined way to make random problems with specific N and R. How did they check them?
They used a popular, well-regarded open-source SAT solver called Minisat.
Minisat. Okay.
For each of those thousands of generated instances, they fed it to Minisat. Minisat would then work on it and report back one of 2 things. Satisfiable, meaning it found a solution.
Found a way to make it true.
Yep. Or unsatisfiable, meaning it proved no solution exists.
Okay. And they measured the time, too.
Yes, they recorded the time Minisat took to reach that conclusion, though they put a time limit, a cutoff of 60 seconds per instance, just in case some were incredibly hard.
Sensible. And I think you mentioned they ran this on Google Colab, so the exact time in seconds isn't the main point.
Exactly right. The absolute speed depends heavily on the specific computer hardware. What they focused on were the relative trends. How does the chance of being satisfiable change as R changes? How does the average solving time change across those different R values?
So after running all those instances, they'd calculate averages for each NR setting.
Correct. For each pair, they calculated the satisfiability ratio, just the fraction of the 100 instances that came back satisfiable.
So like 85 out of 100 means a ratio of 0.85.
Precisely. And they also calculated the average solving time for those 100 instances.
All right, let's get to the results. What did that satisfiability ratio show as they increased the constraint density?
Well, the primary finding here strongly backed up what others had seen before.
Ah.
As error increases, the satisfiability ratio drops very sharply. It's definitely not a gentle, linear
A
decrease.
steep drop. And where did they see this drop happening in their experiments?
They really pinpointed the critical region in their data. The sharpest part of the drop was consistently happening right around RA 4.2 to 4.3.
Very close to that previous estimate of 4.26.
Exactly. It lines up very well.
And was it like falling off a cliff or more of a curve?
They described the shape of that drop as sigmoid-like.
Sigmoid, like an S-curve.
Yeah, think of a stretched out S, but falling downwards. It starts high, drops rapidly in the middle, then flattens out at the bottom. That S shape is actually a hallmark of phase transitions in lots of different systems.
Interesting. Okay, what about the size of the problem? Did changing in the number of variables affect this drop?
Ah, yes. This is where it gets really compelling, I think.
How so?
They found that as N got bigger, as the problems got larger, that transition, that drop in satisfiability became much more abrupt, sharper, steeper.
So for bigger problems, the change from likely satisfiable to likely unsatisfiable happens over an even narrower range of R.
Exactly. And not only did it get steeper, but the specific point where the drop was sharpest seemed to converge more tightly towards that theoretical value around R02 or 4.26 as an increased.
Can you give us a feel for how much sharper, like comparing small n to large n?
Sure. Let's look at their examples. For the smallest problems they tested, N20.
Okay.
The satisfiability ratio dropped from about 70% when R was 4.0 down to below 25% when R hit 4.4.
Okay, so a fall of about 45 percentage points over a range of 0.4 in R. Noticeable.
Right. Now, contrast that with a larger problem size, say N60.
Okay, bigger problem.
Over that exact same small increase in density from R4.0 to R4.4,
Uh-huh.
the satisfiability ratio plummeted from roughly 90% satisfiable all the way down to under 5% satisfiable.
Wow. 90% down to less than 5% in that tiny 0.4 window of R. That's a massive cliff.
It's incredibly dramatic. It shows how much more sensitive larger problems are to this critical density.
And for the biggest ones, N100.
Even tighter. They found the ratio went from 80% down to 10% within an even narrower band, roughly between R4.16 and R4.28.
So that really nails down the location near 4.26 and shows just how knife-edge that transition becomes for large-scale problems.
Absolutely. It confirms the convergence and the increasing steepness really clearly.
Okay, so satisfiability basically falls off a cliff around R4.26, especially for big problems.
Yeah.
What are the other thing they measured, the time it took to solve, or how did that behave?
Right, the solving time. It also showed a very distinct nonlinear pattern related to R. It didn't just get steadily slower as they added constraints, which you might naively expect.
Okay, so what did it do?
Well, for low values of R, let's say below 3.5 or so.
Where things are mostly satisfiable.
Exactly. The formulas are usually pretty easy to satisfy. There are lots of solutions floating around, so Minisat tends to find one very quickly. Solving time is low.
Makes sense. What about at the other end for high R, say above 5.0?
There, the formulas are overwhelmingly likely to be unsatisfiable. No solution exists.
Right.
And it turns out that modern SAT solvers are often quite good at proving unsatisfiability when the constraints are really dense and conflicting. They can detect contradictions relatively quickly.
So wait, low R is fast because solutions are easy to find. High R is also relatively fast because proving no solution exists is efficient.
That's often the case, yes. The solver can prune the search space effectively.
Okay, so if it's fast at low R and fast at high R, what happens in the middle? Right around that critical transition point, R 4.2.
That's exactly where the solving time spikes dramatically.
It gets hardest right at the edge.
Precisely. That critical region is where the solver has the toughest time. The instances there are kind of on the fence, not obviously satisfiable, not obviously unsatisfiable.
Why would that be the hardest point? It feels a bit counterintuitive.
It's a fascinating phenomenon seen in many complex systems near phase transitions. Think of it like this. When R low, the solution space is vast and maybe well connected, easy to navigate.
Okay.
When R is very high, the space might be empty, but the conflicts make it obviously empty in a way the solver can detect quickly through logical deductions.
Right.
But right at that critical density. The remaining potential solutions might be sparse, maybe forming isolated islands in a very rugged search landscape. Or the constraints are balanced in such a way that they conflict, but not so strongly that the solver can quickly prove unsatisfiability. It has to do a lot more searching.
It's like the solver gets stuck exploring difficult paths.
Exactly. It has to work much, much harder before it can either find one of those rare solutions or exhaust all possibilities to prove none exist. It's sometimes called the region of peak computational complexity, or more poetically, the edge of chaos.
Wow. Do the actual experimental numbers show this peak clearly?
Oh, absolutely. For instance, with N60, the average solving time hit its peak right around our world 4.2. It was about 0.00005 seconds.
Which sounds tiny.
It is tiny in absolute terms, yes, but compared to the average times in the lower regions, like Argyle 3.0, or higher R regions, like 5.0, which were often well below 0.00001 seconds. So the peak was several times higher.
A definite spike.
A very clear spike. And for the larger N100 problems, the peak was even more pronounced. It occurred near R or 4.3 and reached about 0.00035 seconds on average.
So significantly higher again.
Yes, much higher than the surrounding regions, and just like the steepness of the satisfiability drop, this computational time spike also tends to get larger and sharper as the problem size increases. Bigger problems have a higher peak difficulty right at the transition.
Okay, so the experiment clearly shows this sharp threshold in satisfiability and a corresponding peak in computational difficulty right at that same point, around R 4.26. But the study it takes this a step further, right? It doesn't just report the numbers, it interprets them using ideas from other fields.
Yes, exactly. This is where they connect it to broader concepts, particularly the idea of emergence.
Emergence, okay.
They argue that these results aren't just about how hard the problem is for an algorithm. They suggest it's evidence of something deeper, a structural phase transition actually happening within the space of possible solutions itself.
A structural transition. What does that mean for a bunch of true-false assignments?
It means that sharp drop in satisfiability around R 4.2 isn't just viewed as fewer solutions left. It's interpreted as the point where the sheer density of constraints piling up causes the entire system, the underlying structure of potential solutions, to fundamentally shift its character.
Wow.
It changes the topology of the solution space. Think about its shape, how solutions, if any, relate to each other, how constrained it is. The paper argues the very identity of the problem transforms at that threshold.
And they see similar transformations elsewhere.
Yes, that's the core of the interdisciplinary argument. They explicitly draw parallels to those phase transitions in physics. Water to ice is the classic one.
Right.
But also, crucially, to phenomena studied in complex systems theory, the idea of emergence.
What kind of complex systems? Give me some examples.
Well, the paper mentions things like how grammatical rules seem to emerge and solidify in the evolution of a language, or how social norms suddenly crystallize within a group or society. Collective behavior shifts in economics, like market crashes. Even on a much grander scale, the appearance of new species in biological evolution, triggered by accumulated environmental pressures or genetic changes.
Those seem like very different things from a logic formula.
They are on the surface, but the study suggests they share a common underlying pattern. These are all examples, they argue, of emergent systems. Meaning systems where you have lots of individual components or interactions accumulating.
Like the constraints in SAT.
Exactly, like the constraints. And then past a certain point, a certain density or threshold, a sudden, qualitatively new, higher-level structure or pattern appears. It wasn't explicitly programmed in, it emerges from the interactions.
So the SAT case, the constraints are the micro level.
Right.
And the sudden change in the structure of the solution space, whether it's connected, fragmented, or empty, that's the macro pattern that emerges.
That's precisely the interpretation. The accumulation of information in the form of constraints fundamentally alters the landscape where solutions might exist. It creates a new pattern, a new structure. The paper uses phrases like a micro to macro transition, or even data becomes structure.
Data becomes structure. That's a powerful phrase.
It is. It suggests that information itself, when it reaches a critical density, can organize into new forms.
What's the real significance of drawing this link between, say, solving a logic puzzle and the emergence of social norms or biological species.
Well, the study proposes this approach as a way to build an interdisciplinary bridge between computational theory, information science, complex systems thinking, and maybe even disciplines in the humanities or social sciences that study complex cultural or social structures.
Wow.
By suggesting that the kind of quantitative analysis we can do on SAT problems, identifying these sharp thresholds, measuring the properties around them, might offer a framework, perhaps even a quantitative one eventually.
A framework for understanding similar points of sudden change or emergence in all these other diverse systems.
That's the potential implication they're hinting at. It's about looking for universal principles governing how complexity arises and how systems undergo these fundamental shifts in organization.
Okay, that's a really fascinating perspective. Let's try and wrap this deep dive up. What are the absolute key takeaways from the study and our discussion?
I think the first is the strong experimental confirmation. For random 3 SAT problems, there's a very sharp transition point, an emergence point, driven by constraint density R.
Right around R equals 4.2 to 4.3.
Exactly. At that point, the probability of finding a solution drops dramatically, almost vertically, for large problems. And right at that same critical point, the computational effort needed to solve the problem peaks significantly.
And this whole phenomenon gets sharper, more pronounced as the problems get bigger.
Yes, the transition gets steeper and the computational peak gets higher, converging towards that theoretical threshold.
And the bigger picture implication, the connection to emergence.
The key implication is that this likely signals more than just algorithmic difficulty. It points towards a fundamental structural transformation happening within the problem's abstract solution space itself.
A phase transition.
A phase transition, yes. And this links these computational problems directly to the kinds of emergent phenomena and critical thresholds we observe in physics, biology, economics, maybe even social systems.
So why should someone listening, maybe someone who isn't, neck deep in computer science theory, care about this? What's the relevance?
Well, I think understanding how these fundamental transitions happen, how complex structures can suddenly emerge from just accumulating simple rules or elements.
Even in abstract math.
Right, even there. It gives us potential insights into how complexity arises and evolves more generally, how systems shift between different states or phases. It's a glimpse into how information, constraints, and density can literally structure reality, and that principle might apply far beyond SAT solvers.
It really does make you stop and think, doesn't it? Consider how that simple act of just adding rules, adding bits of information, adding constraints, even in a purely mathematical system like SAT, can lead not just to gradual difficulty, but to sudden qualitative shifts. The emergence of entirely new structures, new behaviors, new impossibilities. So a final thought for you, the listener. Where else in your life or in the world around you, maybe in organizations and learning a skill and social trends, anywhere might you see similar emergence points? Places where just accumulating elements, information, or constraints past a certain density or threshold causes a sudden fundamental change in the whole system.